Well, ladies and gentlemen, welcome to the Leonard Nimoy Event Horizon Theater and our very special lecture with Dr. Richard Ellis. I'm Dr. David Reitzel. I'm the astronomical lecturer here at Griffith Observatory, and it has been a long time since we've had a live lecture here in the Leonard Nimoy Event Horizon. We had one All Space Considered last month. We've moved it to the third Thursday mostly. We have one coming up on April 20th, but this is our first guest lecture. And boy, do we have a great one for you. We couldn't have started off a return to guest lectures with something more exciting than this, in my opinion. Tonight, like I said, we have Dr. Richard Ellis. He is a professor at University College London and also Caltech. He is a world-renowned expert in galaxies in the early universe, some of the very first galaxies that were being formed. He's won the gold medal of the Royal Astronomical Society, as well as being a fellow of the Royal Astronomical Society. I talked about Caroline Herschel last month at All Space Considered. She won the gold medal of the Royal Astronomical Society. So this is not exactly an easy thing to win. And tonight, we're just thrilled to get some of the very first results from JWST. And then you also have an opportunity to pick up a copy of his book, When Galaxies Were Born, and have him sign it. It's a great memento of this lecture. Makes a great gift. I know we're not in gift-giving season exactly, but I've got some folks in mind that I know will enjoy it. So pick up a copy, and we'll be signing those afterwards. But right now, I'd like to invite Dr. Richard Ellis up here now to present his lecture, The Quest for Cosmic Dawn, the first results from the James Webb Space Telescope. Let's welcome Dr. Ellis.
Thank you very much. Thank you very much, David, for those very kind words. It's great to be back. I used to be at Caltech permanently, and I came here and gave lectures a couple of times before. And thank you very much for struggling with the traffic. I nearly didn't make it myself. I was stationary for about half an hour. But anyway, we're all here, and it's just great to give an in-person lecture, isn't it? There's no substitute for an in-person lecture, so it's great to see you all here. So it is a very exciting time in astronomy at the moment because of the launch of the James Webb Space Telescope. How many people watched the launch of James Webb on Christmas Day? There you go, aficionados. Excellent. Okay. This is the first deep image taken with the James Webb Space Telescope. It is an 8-hour exposure of a cluster of galaxies. The white objects here are all galaxies at the same distance. This is a foreground star, obviously. But the interesting thing about this image is not this cluster of galaxies, but all the stretched and distorted objects in red that are behind this cluster of galaxies. And they are being magnified and distorted by the gravity in this cluster of galaxies. Just like a lens, an optical lens, is focusing light, so Einstein predicted that light would be bent by gravity, by gravitational objects. Objects with matter would bend light. And so it's this beautiful illustration of this that was introduced by your president. Now, I think it's fair to say your president didn't quite completely grasp the physics of what was going on in this image. But, we'll forgive him for that because he had other things on his mind at that time. So this talk is about going back in time. Astronomers are unique in that they can time travel. We all have our, idea of what we would like to go back and witness. I don't know. I'd like to go back and witness the pyramids being built. Maybe you'd like to go back and see William Shakespeare writing his plays or something. Or maybe a famous football match that you missed or something like that. Well, astronomers can look back in time because light travels at a fixed speed and the universe is a very, very big place. And so when we look at the sun, we see the sun as it was 8 minutes ago. That's how long a light ray takes to reach us from the sun. When we look at the nearest star, we see that star as it was 4 years ago. That's the light travel time from the nearest star to the Earth. But the situation is very different when we use a big, powerful telescope like the Hubble Space Telescope and now the James Webb Space Telescope. we're looking back not millions of years, not even a billion years, but over 13 billion years into the past. And so the story of my talk is piecing together the evolution, not of an individual galaxy. We don't live long enough to see any galaxy change. But of course, we can piece together the population seen at different times in cosmic history. So when we take a picture, we want to time slice that picture into different times and then compare the picture seen at different points in cosmic history. So we need a marker. We need to know how far we're looking, how far back we're looking. This is the only equation in my book, and it's the only equation in my talk, and you don't need to know it anyway. Here's a galaxy far away, and we're here, and here's a blue light ray that starts on its journey towards us. And the universe is expanding. And as you might think that the galaxies are moving as projectiles in empty space, or pre-existing space, that's not the correct view of the expansion of the universe. It's space itself that is expanding. And so as this light ray travels towards us, the space in between that galaxy and the Earth is stretched. And along with that stretching, the light ray is stretched as well into a red light ray. And if we can measure by how much that light ray has been stretched, for example, by comparing features that we know in the laboratory, we know exactly what wavelengths or frequencies they're at, then we can measure that redshift. And it is a measure of by how much the universe has expanded since light left that object. So if we can measure this redshift, how much the shift in the wavelength from the blue to the red, then we can convert that into how far back in time we're looking. And astronomers have this very useful phrase, lookback time, which is a measure of by how much we're looking back in time. So my colleagues and I and many astronomers in the UK and the United States and elsewhere have pieced together this wonderful story of the evolution of galaxies. So today, we see two kinds of galaxies. We see this kind of galaxy, which is what we call an elliptical galaxy. You can see it's very uniform. The stars all have the same color, and there are no features. And then we see a spiral galaxy like this one here, which has a nucleus. It has spiral arms that are bluer, and our Milky Way is also a spiral galaxy. So these are the beautiful galaxies that we see in the local universe. If we look back in time, using this technique that I mentioned, measuring the redshift of the galaxy and converting that into the age of the universe at the time that the light left that galaxy, you can see that these two galaxies resemble the elliptical galaxy that we see today. These galaxies look a little bit, maybe not quite so elegant, but you can see they have a nucleus and they have blue features, so these are probably going to evolve into spiral galaxies. And, but if we go back to when the universe was only 1 to 2 billion years old, you can see things change dramatically. These galaxies are not symmetric. They have multiple components, as if they're coalescing and still assembling. They're physically smaller, and they just lack the symmetry that we see in nearby galaxies. So over the last 20 years, largely with Hubble, we've managed to piece together a broad view of how galaxies are assembling by merging with one another, how they settle into these regular forms over cosmic time. And this is about 90% of the history of the universe. But the title of my book, Cosmic Dawn, relates to looking sufficiently far back in time to see when galaxies first emerged from darkness. So this is obviously a cartoon. You see time running from left to right. This is the Big Bang, where the universe first came into existence. And after about 370,000 years, the universe basically cooled, and the hydrogen atom in gas formed for the very first time. But the universe was dark. There were no stars, no galaxies. We call this the Dark Ages. Astronomers are very fond of the adjective dark. You've probably heard of dark matter, dark energy, dark ages. It's very useful. It adds an air of mystery, which is very useful in raising money, for getting grants and so forth. So these gas clouds collapse under gravity. And as they collapse, they get hotter, just like the bicycle tire gets hotter when you compress the air in pumping up a bicycle tire. Eventually, the hydrogen gets so hot that it ignites nuclear fusion. And that's the process by which the sun shines. Hydrogen is being converted into helium. And so the universe is bathed in starlight for the first time. Now, at that point, you might think that that's just a detail, but because all of the conversion of hydrogen to helium and then later helium to carbon, all the way in which stars shine and live their lives, is producing the chemistry that we see around us today. Everything in this room, the iron in your blood, the calcium in your bones, the steel in the chairs, and every fabric here is made of atoms that were synthesized in stars. So cosmic dawn is the beginning of you and me in a way, because it's the beginning of the chemistry that leads ultimately to life. So it's an unfortunate fact, we live in a world with theoretical astronomers. They have no need for observations. All they need is a computer. And here's a simulation from one of my theoretical astronomers of cosmic dawn. So you can see, if you've got good eyesight, time is running in millions of years. And what you see is hydrogen clouds. The blue are the hydrogen clouds with a filamentary structure. And then as they collapse, they form these stars, and these stars explode at the end of their lives. These stars are very massive, and they explode very quickly after a few million years, which is very quick for an astronomer. And you can see it's a very beautiful simulation. So if we were able, and of course we're not at the moment, if we were able to witness this, it could be a very dramatic moment. Now, how far back do we have to look? This is that complicated topic, Redshift again, and this is the date of publication, and this is the age of the universe that corresponds to that redshift. So today, galaxies that we see around us today are living in a universe that's 13.8 billion years old. And in 1960, when the mighty Palomar telescope was the biggest telescope in the world, the most distant galaxy, when I was a student, had a redshift of 0.5. And now you can see, thanks to progress, which I'll describe in technology and building bigger telescopes, faster detectors, and so forth, you can see that we've pushed back the frontiers to a redshift of 10 when the universe was in its infancy, 5%, 3% of its present age. So, my book goes through this revolution in exploring and directly witnessing the past. I showed this slide frequently in my talks as recently as April and May of last year. It's already out of date. It's out of date because in the space of only 6 months, James Webb has revolutionized our subject, and I'll tell you more about that shortly. So the questions that we now face are, when did this cosmic dawn occur? Can we determine when in the cosmic history the universe first shone in stars? And most excitingly, can we witness this directly? Will we be able to recognize a baby galaxy that's forming for the first time out of darkness? So those are the two big challenges that we face today. So this is me, believe it or not. Go back to 1956, and I walk into my little public library in North Wales, and I pick up this book called Out into Space. It's written by this eccentric man, Patrick Moore, no longer with us, became Sir Patrick Moore. He looks very much like what many people think astronomers look like, you know, eccentric, monocle, but he was an amazing man. And I read this book. It's a fictional story about two children that go and visit their uncle who's got a telescope. And obviously it's a children's book. And it inspired me at the age of 6 to become an astronomer. And I've been very lucky that, you know, many people struggle with trying to determine what job they should do. I never wavered in my ambition. I knew from the age of 6 that there was all this up there to be explored. And he had a television program called The Sky at Night. It was on very late at night, but it was a regular program, and I appeared on it, not as a 6-year-old, I should add, but when I was 40 or so. And I told him about this book, and he gave me his personal copy and signed it. So that was a very nice. So, you know, I've been very fortunate to use all the big telescopes in the world. I'm going to go through a little bit of the history that I wasn't involved in with the mighty Palomar telescope. How many people have been up to Palomar? If you haven't, you really should go. The observatory is now open again. It's a beautiful day out. It's a 2.5 hour drive from Los Angeles, but it's a beautiful place, lovely mountain, and it's a fantastic observatory. My career started when Prince Charles, now King Charles, opened this telescope in Australia, the Anglo-Australian telescope. And when I was in my 30s and 40s, I would fly. I wouldn't think twice about flying from London to Australia, you know, sometimes just for 2 or 3 nights on a telescope. That was the exciting time. And then Britain built telescopes in the Canary Islands, William Herschel telescope. Then, as David mentioned, I emigrated to Pasadena, and I started using the Keck telescopes. And then finally, I moved back to Europe, and now I also use the European southern observatories, large telescopes, in the Atacama Desert. Those were all ground-based telescopes. There are space telescopes, too. Everybody's heard of Hubble. There's the Spitzer Space Telescope, which is finished now, but it plays a very important part in the story. And now we have this amazing telescope, and more on that later. This man, George Ellery Hale, was an amazing man who single-handedly raised funds from wealthy donors to build a succession of the largest telescopes in the world, including the Palomar 200-inch or 5-meter Hale reflector named after him. Sadly, he never lived long enough to see it completed. When I was 8, my sister and I had an encyclopedia, and in this encyclopedia is this cutout picture. It didn't say which telescope it was, it just said a modern observatory. And of course it is, as you can see, the Palomar 200-inch. When we say 200-inch, we mean the diameter of the primary mirror. This is the power of the telescope. The larger the mirror, the bigger the light gathering power, and hence for 40 years this was an unrivaled facility. And little did I know when I was 8 years old that when I moved to Caltech that I would eventually become the director of this observatory. Now Hale was one of the first people to really grasped this idea of looking back in time. He hired Edwin Hubble, but he also hired this man, Harlow Shapley, who became head of Harvard astronomy. And with the 60-inch telescope, which was the biggest at the time, Shapley looked and measured the distance to this star cluster. And it was a whopping 36,000 light years. Now, compared to what we're doing with James Webb, this is peanuts. But Hale realized that we were looking back in time. I mean, he actually recognized that we could determine the history of the universe. And he used this to raise $6 million from the Rockefeller Foundation to build the Palomar Observatory. It was the biggest donation to any scientific endeavor at the time, not just astronomy. And here's the quote that he used in raising the money. "Like buried treasures, the outposts of the universe have beckoned the adventurous from immemorial times." It's a perfect quote for my book. So here's Hubble, very strange man. He wanted to be a lawyer. He moved to Oxford in England, and then came back with an affected English accent that really annoyed his Californian colleagues. And very sadly, he had a heart attack more or less as the 200-inch telescope came online and was forbidden to go observing by his doctor for several years. So he handed the baton to this guy, Alan Sandage, who died about 12 years ago. And I remember when I was here at Caltech very fondly. And Hubble told Sandage, "You've got to go and find more and more distant galaxies because we want to measure the rate at which the universe is slowing down. And to do that, you need to measure the distance and the redshift, two separate things." And then, incredibly, there was a competitor from the same city. So Caltech and Carnegie are both in Pasadena. Hubble was in Carnegie Observatories. James Gunn was a bright young spark in Caltech. And they were doing the same project competitively with the same telescope. Quite amazing, really. And there's an interview with Sandage by Dennis Overby, who used to write for the New York Times, where they ask Sandage, who do you think are the good, best astronomers today? And he said, well, young Jim Gunn's doing pretty well. If he keeps it up, he could be number 2. Then along came a woman, Beatrice Tinsley, a New Zealander. And she visited Caltech, and she pointed out to Jim Gunn that what they were trying to do with the 200-inch was futile. You can't estimate the distance to a galaxy by its brightness, because galaxies are made of stars, and those stars evolve, and so the galaxy will evolve. And so when you look back in time, a galaxy may be brighter or dimmer in the past, and therefore you can't use the brightness of a galaxy to estimate its distance, which is what both of these very famous astronomers were doing. So there was a complete paradigm shift when I started my career in the 70s. We're really looking at the evolution of galaxies. We're not using them to measure the expansion history of the universe. And I've been very fortunate that during this period there's been huge revolution in technology. So Sandage and Hubble were using photographic plates. Now you must have seen movies where you put a glass plate in, the photographer has a hood, and then he removes a shutter, he exposes, and then he processes this photographic plate. That's how astronomy was done until the 1970s. And then along came the digital detector that's in your iPhone, the CCD, the charge-coupled device. And now we can make mosaics of these CCDs and have megapixels, this particular camera on the Japanese telescope is an 870 megapixel detector. It's 30 to 40 times more sensitive than the photographic plate. So as soon as these detectors appeared on telescopes, it's like having a telescope that's 30 to 40 times more powerful. I told you about mirrors, bigger mirrors. So this is one of the Gemini mirrors. It's 8 meters across compared to 5 meters for the Hale telescope. So it's much more powerful. The Keck telescope is 10 meters across. So that's twice the size. in diameter, 4 times, because the area is what really matters, 4 times more powerful than the Palomar telescope. And if you look closely, it is a segmented mirror telescope. There are hexagonal segments that are all, 36 of them, each a meter across, that are all being carefully orchestrated in the shape of a primary mirror. And robotics made a big difference. And, you know, Hubble, Sandage, and Jim Gunn were measuring these redshifts one by one. And then along came fiber optics. It's really just like plumbing. These fibers, you know, convey the signal from a galaxy. So what you see is a brass plate with holes drilled in it with the precise position of, say, 50 or 100 galaxies. And you collect these and you measure the redshifts and spectra of 100 galaxies in the time it used to take just to measure one. So obviously that's another revolution in exploring the early universe. Now, in this picture, this is me here, and this is my colleague, and what we're doing is we're plugging these fibers into the holes, and each fiber has a number, and each hole, of course, has a galaxy number. And, you know, woe betide you if you lose that piece of paper that tells you which fiber goes in which hole, otherwise you won't know what you've been observing. So it was just a matter of time before we automated it. So we built a robot, and the fibers are running out here tangentially for the experts. The light comes from above, and there's a tiny right-angled prism that reflects the light into each fiber. And largely as a publicity stunt, we made this robot draw a map of Australia, to which the usual response was, "What about Tasmania?" So how do we find the most distant galaxies? Well, we need a shortcut. I mean, unfortunately, the faintest objects are not necessarily the most distant. And so the trick, which was pioneered by one of my colleagues at Caltech, Chuck Steidel, is that the universe is full of hydrogen. Hydrogen is not only in galaxies, but it's in the space in between galaxies as well. And hydrogen absorbs in the ultraviolet. And so you can see this particular galaxy is visible in a red filter, is visible in a green filter, and then it disappears in the ultraviolet. And that's a telltale sign that the light has been redshifted so that this ultraviolet disappearance is clear. You can see the other objects, most of them are visible in all 3 filters. So here's a little video that might make it a little bit clearer. These are all the color filters in Hubble Space Telescope. So this is these are blue filters, here's a green filter, yellow, red, and infrared. And this galaxy is being progressively redshifted, so we're looking at it further and further back in time. And if we want to know how far back in time we're looking, all we have to do is calculate at which filter the galaxy disappears, and that tells us how far away it is. This is what we call photometric redshift. It's no substitute for a true spectrum, and it gives approximate redshifts, and it can be wrong, and we'll come back to that later. Now, just a little interlude. What's it like to observe on a big telescope? Well, you know, I still get a fantastic kick. You know, I'm a romantic at heart. I mean, basically, I stand on a mountain far from home, I watch the sunset, and then I go into the observatory, hoping to make a discovery. And of course, if you make a discovery in real time, it's fantastic. The students that I've had are inspired by going to the telescope. It's not always possible, of course. Sometimes it's too expensive, so you have to observe remotely. But I'm a big fan of going to the telescope, working at the coal face, if you like, and having a great time making a discovery. Now, there is cloudy nights. This is a cloudy night photograph. You fly all the way to Hawaii or Chile, and it's a cloudy night. This guy, these are all 3 of my former students. This guy's very happy because he's finished his thesis. This guy's Italian. I don't know, they're always happy, Italian. And this guy with a forlorn look on his face is, this is his fourth cloudy night and his thesis is going down the drain. And my job as professor is to buy the pizza, the bottles of wine, and that's, I think, why this photograph is slightly out of focus. So how far did we look with Hubble? Well, there's two techniques. One is very simple. You point Hubble in a not particularly interesting area of sky, and you expose for 2 weeks. And that was what is called the ultra-deep field. Now, of course, there was a Hubble deep field, and there was a Hubble very deep field, and then finally we did the ultra-deep field. And it was a collaboration with the Scots. So this is at the Royal Observatory in Edinburgh. And this is the image. It's 1/10 of the diameter of the full moon. It's still the deepest image taken with Hubble. These galaxies, I don't know if you can see with numbers here, are the most distant. And this one, we thought, was at a redshift of nearly 12. We weren't very sure, but I want you to remember that galaxy because it was the most distant that we thought we had found. The other technique is this bending of light. No guesses as to who this is. My wife, some years ago, gave me an Einstein calendar. You know, every month there was a picture of Einstein doing something different. You know, Einstein on a bicycle, Einstein by the blackboard. Then I realized by the time we got to April, he only had one suit. So he was always wearing the same suit. So this guy, Eddington, Sir Arthur Eddington, a theorist, but very wisely became an observer, took a photograph at the eclipse, which demonstrated that the stars by the sun were not at the same position when the sun was in the way. The light had been bent by the mass of the sun. And this verified Einstein's theory that light can be bent by massive objects. And we call this gravitational lensing. And we can use it, of course, like that Joe Biden image I showed you at the beginning, to magnify distant objects, just like an optical lens. It's like having a free telescope. All you've got to do, you've got to steer through a cluster to use this wonderful technique. Here's a simulation of a transparent lens moving across a field of the sky. And you can see, depending on its alignment with background objects, you can get either rings or distorted objects. And the mathematics of this has been very well developed. So, you know, we can look through clusters of galaxies. This is a real image now with Hubble, and we can see images of the same galaxy in different places in the sky, like a mirage. And if we know the magnification, we can go deeper with this technique than we can with that ultra-deep field. So, two very different methods. Point Hubble in a blank area of sky, open the shutter, point Hubble through a foreground cluster of galaxies that acts as a telephoto lens. And the answer is, they give the same answer. The census of galaxies is falling. As you go further back in time towards the beginning, the number of galaxies is diminishing. For experts, this is a logarithmic scale. So from here to here is a factor of 1,000. And so cosmic dawn would be, well, you know, where there are no more galaxies. So it would be somewhere down here. Now, there were two rival groups doing this. This guy here is from Switzerland, but then the Scots were doing it too, and there were disagreements. You know, it wasn't clear whether this curve is going down gradually or whether it's going more steeply. Theorists much preferred this curve here, going steeper, which would suggest we would run out of galaxies when the universe was about 300, 400 million years old, redshift of about 12 or so. It's out of date already, okay? Just in 6 months. There's one other technique that we developed when I got to London in 2017, and that is to look at the oldest galaxy, seen when the universe was very young, and measure its age. So the analogy I use here is you're walking down the street, and you meet a 4-year-old boy. You weren't present at his birth, but if you can determine how old he is, then you know when he was born. So back to this slide, if you can find a galaxy here and say, well, how long have you been around? You know, have you been around for 100 million years, 200 million years, 300 million years? Then although you don't witness cosmic dawn, you can estimate when it might have happened. And that's exactly what we did. We looked at this galaxy using a technique that estimated this break, which depends on the age of the stars. But to use this technique, we had to be absolutely sure of the redshift of this galaxy. It was thought to be around a redshift of 9, so that's about here, when the universe was about 600 million years old or so. But we needed to get that redshift very, very precisely. And so we went to the Chilean telescope, the one in the Atacama Desert, no trees. In some places, it's never rained in recorded history in the Atacama Desert. Here's that galaxy. And here we are standing in front of this monster telescope, 4 8-meter telescopes, the very large telescope. One has to admit the Europeans know how to live. This is the only observatory with a swimming pool. We estimated 6 galaxies, and we estimated their ages, and we predict, before the launch of James Webb, that cosmic dawn occurred 250 to 350 or 400 million years after the Big Bang. And we were very excited because that's precisely the period that James Webb can explore. So here it is. So just before lockdown, in fact, literally a month before lockdown, I was in Pasadena and went to see the James Webb Space Telescope in El Segundo at Northrop Grumman's facility. There's a human here, to give you some idea of the scale. Seeing this is like a religious experience. It's a gigantic thing. It's got 18 gold-coated beryllium mirror segments. It's a 6.5-meter telescope, so it's bigger than the Palomar telescope, and yet, of course, it's launched into space. And to launch it into space, the mirrors have to be folded so that they fit in this nose cone of an Ariane rocket. I was the only European on the committee in 1996 that recommended this facility. 1996 to 2021, you know, that's patience, isn't it? Waiting for a facility like this. Think of all the thousands of people who worked on this telescope during that period. It was like, you know, if you go back and look at the building of the cathedrals in Europe or England, you know, entire families would move and spend their entire life in a foreign place just building a cathedral, you know. So this is the equivalent now. These telescopes are our cathedrals, right? It was delayed, so there's some smart man or woman plotted, you know, the planned launch date against the current date, you know, and it looked like it would never be launched. It was always being delayed, you know, and I think it's written at the bottom here, well, at least the slope is less than 1, you know. It was not just disappearing into infinity. But $10 billion, and here it is hanging by a hook, all right? You know, you have to have some courage. And then it goes in the nose cone of this Ariane European rocket. We all watched it. It nearly spoiled my Christmas lunch, but I managed to keep calm. And here's the last view that we will ever have of it, because it can't be visited. It's 1.5 million kilometers away. It's not orbiting the Earth. Hubble orbits the Earth. James Webb orbits the Sun. It's in a very special position. It's here. Here's the Earth. Here's the Sun. The combined gravitational pull of the Earth and the Sun equal the pull that the Earth gets from the Sun. So what that means is that it's in sync. It goes around the Sun with the same period as the Earth. So it's always close to the Earth, even though it's further out from the Sun. And of course, it's been a huge success. So here's the latest. nearly done. This is that census plot before, okay? Here was the, the Swiss version of the story, and here was the Scottish version of the story. This was the horizon of Hubble, and what we found is, as we had predicted, we found galaxies further back in time, back to when the universe was about 350 million years old. There have been some retractions. Let me tell you, since July, there have been 70 papers on the internet on distant galaxies, and I've read them all, seriously. And they're all very exciting. Not all of them are perfectly accurate, but it's just great fun. There have been some retractions. There have been galaxies at Redshift 16 that we now think are not so far away. But generally speaking, this result looks pretty robust, as I'll explain in a moment. I told you that this was theory. The theorists love this decline beyond a redshift of 8 to be very steep. Why is that? Well, it's because theorists think that these gas clouds should convert into stars with a constant efficiency. And these galaxies are clearly not doing that. They're too bright. So they're forming their stars much more efficiently than the theoretical models predict. And we don't know why. It's very exciting. I was at a conference in Italy 2 weeks ago. This was the whole topic of one day at the meeting, is what's going on here? Why are these galaxies so bright? There have been claims that the galaxies are too massive, but I'm pretty skeptical about that. This guy here in Australia been estimating the masses of these galaxies and claims some of them are more massive than the Milky Way, which would be really very strange given, how little time there's been since the Big Bang to form them. I think most people are skeptical of this result. But the wonderful thing about James Webb compared to Hubble is it has spectrographs on board which allow us to measure the redshifts much more accurately. So let's just recap. This business of using the color filters and figuring out where the galaxy disappears is only approximate. It gives approximate redshift. We use that technique, if you remember my most distant galaxy at 11.9. Well, fortunately, the redshift of that galaxy has been measured. Here's the beautiful spectrum from James Webb. It's at 11.6, pretty close. We said 11.9 plus or minus 0.4. And if you compare the color-based redshifts with the spectroscopic redshifts, you can see that it's pretty good. So I'm pretty confident that these galaxies are at the right place. About 4 of them have now been confirmed beyond Hubble's horizon. So the final thing is this last question. How will we know when we've seen a galaxy that's emerging from darkness? And the answer is chemistry. Remember I told you that these objects that first emerge from darkness are pristine. They just have hydrogen and helium. They don't have the heavy elements that make up you and me. And James Webb has these powerful spectrographs on board. So nuclear burning goes from hydrogen to helium, helium to carbon, carbon, oxygen, silicon, iron, nickel. And look at this. This is just unbelievable. I never thought I'd see this. Here's a spectrum of a galaxy at a redshift of 10.6. Nitrogen, helium, carbon, magnesium, neon. All the chemical elements are there to be seen in this spectrum. So, the ultimate thing is to measure the evolution of the chemistry of these objects as we go further back in time. And that's the Holy Grail of finding cosmic dawn. It won't be easy. It's a long exposures, but James Webb is going to be up there for 15 years, and it's already revolutionized the subject in just 6 months or so. And, I'm an optimist. All the telescopes that I've used have done more than what they predicted when they were first proposed and conceived. I like to say, unlike politicians, astronomers always deliver more than they predicted. Thank you very much.
time for some questions. Does anybody in our audience have a question? Yeah.
What would happen if there were galaxies older than the predicted age of the universe?
Yeah, I will repeat the question for our audience that's at home watching on the internet. So the question was, what would happen if they found galaxies older than what we think the age of the universe is?
Well, the answer is we've already been in that period quite a few years ago, a few decades ago, actually. It causes pandemonium. We would have to, if it was verified, and that's a big if, then we'd have to rethink what we call the standard model. So the standard model has a Big Bang, and the features that we see in the glow from the Big Bang give us a very accurate age of the universe. And if we found an object, say, at a redshift of 10, that couldn't possibly be that young, but is actually older, then it would be a revolution in the subject. The real onus would be for whoever is measuring the age to demonstrate that they really have done a good job. But yeah, it would be exciting. Yeah, but the reason I know this has happened before is that famous man Sandage was measuring the ages of star clusters, and they were thought to be older than the ages of the universe. And then we found that the ages were correct, but our model of the universe changed.
Yeah. Question here in the front.
I've heard of a liquid metal telescope. Are they better than normal telescopes?
Which one, sorry?
Liquid metal.
Oh, yeah.
Yeah, the question was, are liquid metal telescopes better than ones we use with regular mirrors?
They've been built and proposed, but they're not actually delivering. Most telescope builders are skeptical of their utility. The idea is that the rotation creates the surface, so you avoid an expensive polishing, so they're cheaper. But they've been around for maybe 20, 30 years. I know one very famous astronomer swears by them, but they haven't caught on, and they're not in common use.
Yeah. Any other questions? Yeah, right here.
Why do you not think these very early galaxies are as apparently massive as they seem to be?
Yeah, the question is why Dr. Ellis doesn't think the galaxies that some folks have proposed as being very massive are not that massive.
So here's the paper by Labe and his astronomers in Melbourne, and these are the masses that he measured. Here's the conundrum, which really relates back to your question a little bit. Even if you have 100% efficiency of the conversion of gas into stars, you can't, in the time that's available, produce the galaxies that are as massive as these. Now, the reason why I'm skeptical is that I have measured the masses of these galaxies too, as have others, and there's a very sensible paper that contradicts these masses by the group in Arizona. And so I think, as I said, they're skeptics, Unfortunately, astronomers often put out papers that are not 100% correct. Heaven forbid. Don't believe everything you see on the internet.
Yeah. This is, of course, of great concern to folks as they see astronomers publish different results about things.
Yes.
That concerns the public. But this is actually progress.
Yes.
By allowing folks to publish what they think is true, little by little we'll converge on the correct result as we disentangle why are they getting different answers. I have a question for you. What is the galaxy that is the earliest forming one, I guess? Which one has the biggest look-back time that's been confirmed at this point?
I should know the answer. It's around 13.7, something like that. Okay. I can't remember the exact. Yeah, the sad thing is...
So that's just a few hundred
there was this galaxy, I don't have a slide of it, there was a galaxy almost within a month of the launch of James Webb, a month since science observing began with James Webb, last August, there was a paper with a redshift 16.6 galaxy. And then again, following Roy's question, there was a rebuttal paper from a young upstart from Harvard, saying it was probably at a redshift of 5. And then there was a lot of debate, in conferences about whether it was 16.6 or redshift 5. And they got a spectrum 2 weeks ago, and it's 4.9.
Yeah.
So,
Yeah, I was going to ask about that. Any other questions that are on? Yeah, down here in the front.
Having JWST for 15 years is great.
Yes.
But do you think that there's an important role for cosmological discoveries with bigger telescopes from the ground?
Oh yeah, look, this is just one area. This is just, as you know, this is just one area of science, and in fact, this is only one area of science that's being done with James Webb. I mean, James Webb is also doing fantastic work on exoplanets. So there's plenty to do with bigger telescopes. And of course, we've been trying, as you know, to build bigger telescopes than the Keck telescope. And the Europeans, of course, have this extremely large telescope that's going to come online in 2028 or so. So there's a lot of exciting science to be done. In this talk, just to emphasize, I have focused on a very narrow, but I think personally exciting topic.
And
One more question before we finish up here.
what is the overlap in spectral sensitivity between the Kecks or what was it, the Sophia and the 747?
Yeah.
And into the mid-infrared of
Well, from the ground, mid-infrared is very challenged by the warmth of the Earth's atmosphere. So although there are, telescopes and detectors that are going into the mid-infrared from the ground, the sensitivity is far worse than going into space. So the real breakthrough in, people often say, James Webb is a successor to Hubble. It's not really true. Hubble is an optical and ultraviolet telescope. James Webb is an infrared telescope. And really, James Webb is opening up the infrared region. It's like a super Spitzer. Spitzer was an infrared telescope. It's only 40 centimeters or so. So this is a huge step.
the near-infrared.
Yeah.
is-
It goes out to 10 microns. Yeah.
Yeah. So let's thank our speaker one more time. Thank you, Dr. Ellis. And folks, I encourage you to pick up a copy of the book. The gift shop is still open, and you can get a copy of the book, and Richard will be outside on the edge of space signing copies if you have one to be signed. So thank you so much for joining us tonight.
Thank you.